This is my partner in crime, Chris Francis, and we're the Capstone designers for Phoenix Electric Corporation, and we're going to be introducing the fiber optic high voltage equipment control system interface. So we heard about a lot of projects, a lot of really interesting projects, but our project is it serves a vital purpose because it's going to be protecting the power grid. Now, just recently, actually the other day, the Atlanta International Airport's power went out for 11 hours. So Delta alone reported that they lost $50 million. $50 million. So our project, we're trying to eliminate some of the causes, well, not necessarily the causes, some of the vulnerabilities in the power distribution system. So right here behind me, we have the local control cabinet, and there's some high voltage equipment behind it. And next slide. And we're trying to replace the copper cabling to all these high voltage equipment with fiber optics. So what that's going to do is going to provide a more rugged system, right? Because fiber optics are less vulnerable to electromagnetic interference. Actually, they're not vulnerable at all to electromagnetic interference. The cables can't be tampered with whatsoever. If you actually tamper with the cables, it actually destroys the cladding inside of them. So really, it's just a more robust, it's cost-effective, and it's safer. So our anticipated best outcome. So we want flexibility, adaptability, reliability, and it's got to be cost-effective. So what we mean by flexibility is that there's going to be multiple configurations that our product's going to have to be put in place. So it's going to have to be able to be adaptable and seamlessly integrate into these systems. Next is reliability. So the power companies are looking for reliability. They don't want to lose power for any amount of time. That can be catastrophic, as in the loss of $50 million, or potentially the loss of life when you're talking about hospitals and their power. So it has to be really reliable and a robust system. So we're going to have different error checking that's going to be performed, and we're going to be able to know if we lose a fiber optic cable. It also has to be cost effective. What we mean by cost effective is it's not going to add a price tag of $10,000. It's going to be more like $1,000, $2,000 to the system. Okay, so now we're going to get into our design. So since we can't show you our schematic design, we're just going to give you a general overview of our system. So as you can see, we have two distinct cards, right? We got one on the high voltage equipment card and one on the local control cabinet card. And these cards are going to be paired for specific high voltage equipment. They can be separated between 20 to 200 meters in distance. So in the previous slide, we're going to be taking voltages from high voltages to low voltages. So 125 DC down to logic levels, because as you can see in the center here, we have our FPGA that's going to be the heart of the device. Now this FPGA is going to be connected to two transceivers. That's where I was talking about that reliability factor. So we're going to actually have 4 cables, 2 transmit, 2 receive, and they're going to be able to compare each signal with each other. So anytime there's a lack in communication, they're going to know that one of these cables is down. So on the inputs and outputs to this device is going to perform a variety of continuity checks. Basically, that's going to create our virtual wire to our other side, our local cabinet, or our local control cabinet. The local control cabinet also has two transceivers, and that's going to drive different indications that support different functions for the high voltage equipment. Now Chris is going to take us into our key accomplishments.
All right, so our key accomplishments. Part of our initial research is we visited the PEC facility in Canton, Massachusetts, and we got to see a demonstration of how the current configuration actually works. And also, more specifically, we got to see exactly which components our project is going to be replacing. So with our research, we came up with a 2-circuit board design. This is to help cut down space and help cut down cost. We're going to have each card fitting into a 19-inch rack. We're going to have one on the high voltage side, which I have been working on, and we're going to have another card on the local control cabinet side, which Zach has been working on. So with our research, we're going to be working with high voltages. So we need to get 125 volts down to logic level of about 3.3 volts. So we had to create a high to low voltage converter. We're going to get a line voltage regulator to help give us a nice clean signal, make sure our FPGA and board is going to be working properly. So our schematic design, we're going to be designing interfacing circuits. This way, if a customer wants to upgrade their current system, we can easily go in, take out the old stuff, and we can put on our new product, and it should work fairly easily. So we've been designing communication filters as well, and we're going to be using solid state and MOSFET devices to control our signal flow. And at the end of our schematic, we're going to have a comprehensive materials list. It's going to list all the products that are going to be used to go in our project. So that way, it's easy to reproduce. If another company wants it, we can easily make replicas. So broader implications. This is a fairly unique product. There aren't too many companies that use fiber optics to control high voltage switches. The purpose of this project is to protect power transmission companies and make them safer, less susceptible to EMI. And with our product, we'd like to encourage these power companies to use safer products such as this one. So part of our remaining challenges, once we finish our schematic design, we're going to check it for continuity and completeness, make sure all of our circuits are functioning properly. That way, we can send out our design for the PCB to be produced, which is usually a 2 to 3 week process. Now, while that process is going on, we're going to begin our VHDL programming. Once we get our board in, we're going to load our code onto our FPGAs, and we're going to actually power our boards up right here in-house. That way we can make sure they're functioning properly and allow it for easier debugging and troubleshooting of our project. So with this project, there's a few people we'd like to acknowledge. First of is our technical directors, Sandro Silva and Mike Guerra. We'd also like to acknowledge our consulting director, Mike Smith, as well as our Capstone director, Dr. Sunak.
Thank you.